Okay, so now we're recording the thing. And I guess the first thing I'm going to do is I'm going to ask any questions on anything you read, the reading quiz, the videos you viewed, anything like that. You have to unmute yourself to ask a question. And if you have a question later on, you put it in chat. I'll periodically bring my eyes over there, take a look and see what it says, and hopefully address your question that way if you don't want to pipe up verbally. All right, first thing I want to do is share a screen with you like I always do. It seems like I'm always figuring out how to share screens. This should be Canvas. Yep, you should be seeing my Canvas screen. And just two things I guess I want to make sure are clear. That was chapter 1. That was last week. We're now in chapter 2. And since I've just started populating chapter 2 here, motion in one dimension, you kind of see what each class entails in Canvas for you. And I'm either in the, on the side here, either home or modules, you can find all of this. Okay, and so stop moving around, scroll. All right, we'll go gently there. Chapter 2, this is the PowerPoint notes. It's in a PDF document because that renders my equations properly. If I just gave you the PowerPoint, sometimes depending on what equation editor you have, the equations might show up kind of looking wacky. And so I put it, it's a PowerPoint, but it's saved as in a PDF format. Of course, that's the reading quiz you took last night. Viewing the video and the instructions for what to read. If I put a reading quiz in mastering, that won't be a quiz, it'll just be an assignment, okay? The worksheet problems we're gonna be doing today, the one I'll do a couple of, you'll do a couple of, that's always the third document down, and I try to stay true to this. And then the last thing, that's the place where you upload the worksheet for the portions you did, your calculations on Gus the Goose. That's the place where you upload it. And you can see this will be Wednesday's class. I put the PowerPoint up. It's not active yet. If you look at my screen, I haven't published it yet, but there's a video there and the reading assignment. And each time you'll see these chunks of 4 things. I do want to say one thing about the Gus the Goose. And most geese migrated about, I think it was 80 kilometers per hour, and your calculation, I think just about everybody nailed this, was about 99 kilometers per hour. And a lot of you said, yeah, that's close enough. And some of you said, no, you're off by 20 kilometers per hour, and that's too much. And I'd argue 20 kilometers per hour, that's like 20-25% difference between the speed of the nominal migrating goose and the calculation you did. And that's kind of right on the edge. But I would argue one thing. I don't know if any of you are sprinters, but if you had to do a 100-meter dash, sprint, what would your time be? And I can tell you, well, I was never a sprinter. I was a distance runner. But for me, it would have been like 13, 14 seconds, something like that. I suspect most of you are a little faster than that. But let's say we brought in Usain Bolt, for example, to do that same 100-meter. I'm sorry, I'm old. When I ran track, it was yards. 100-meter dash, okay? He'd do it in like 9 seconds, right? Significant difference in speed. And I wouldn't throw out Usain Bolt's measurement just because it was so much faster than what you and I might be able to do. And if you look at the difference there, it would be about a 20% difference. That's a normal variation in abilities of biological species. So I'd kind of go, yeah, that's all right. And sometimes in a physics class, you might be expecting a value in a lab. Like next week in lab, we're going to be measuring the acceleration due to gravity. And, we all hopefully know it's one of those numbers that people have just seen. If you haven't, well, I'll be the first to tell you, it is the acceleration due to gravity near the surface of the Earth is 9.8 meters per second squared. We're going to throw some balls up in the air next week and or drop balls, and we're going to hopefully make a measurement, which allows us to do a little analysis. And we love the number to come out to be exactly 9.8 meters per second squared. But I got to tell you, I've done the experiment myself a couple times, and sometimes I get 11 meters per second squared. Sometimes I get 8 meters per second squared. You're off by 10, 15, sometimes even 20%. And of course, you look at those and you go, in that case, it should be closer. There's no biological species variation here. Is there anything I can do to fix it? Do I look at my data and see there's some problems with it? And if there is, you fix it, but sometimes 15% is the best that the apparatus can do. And in Gus the Goose, I would have said, yeah, that's fine. The nominal goose goes at 80 kilometers per hour. We calculated 99. Hey, Gus is just an exceptional goose, I guess. I didn't take points off for that, but that's just something to remember in a physics class. Sometimes we're doing fairly gross estimates in our models and our calculations, and we're not going to get exactly the answer we got. Now, for you chemists out there, the reason I bring this up at the beginning of the semester, because I know that apparently that's sometimes how you get graded in a chemistry lab. I've actually had students in the past at Washington College tell me, let's say you're supposed to get a particular result for an experiment. I don't know, maybe a pH you're supposed to get at the end is supposed to be 8, and you get 9. Well, that's going to get you one grade, whereas if you measured 8.1, that would get you another grade. If all those students lied to me and that's not how the chemists grade, well, good, because they shouldn't. It's more about, did you do the procedure right? Were you reasonably careful in taking your data? And did you do your calculations correct? And if you met those 3 goals, even if your numbers don't match exactly in your lab, I'm not going to take points off unless my sense is that, you just phoned it in, okay? But merely trying to match a nominal number or an expected number is not the goal in a physics lab. It's really not what we're all about. On the subject of labs, since I brought it up, I just scrolled down a little bit to this week's lab. And those of you who are on Wednesday, okay, you'll meet at your normal time. Professor Kem is your lab group moderator, teacher, whatever you want to say. You show up, he's going to give just a short, maybe 10-minute introduction to what the lab is expected of you. And the first thing here is the lab handout. You can see it's a joint effort between the 2 of us. That's why both of our initials are on this version of the lab. Here's a video you're going to watch. Here's a logger profile that you're going to work with. And then this is where you submit. I made a little template in the lab handout. You put your numbers that you measured in there, your calculations you put in there, and then you upload that. Within the lab handout, you're going to watch this video right here, which I was able to put into the Canvas Studio, and so I can link right to it. There'll also be 2 videos that you're going to go to YouTube for. I couldn't get the links to work in Canvas. You're just going to have to cut them and paste them from the lab handout and paste them into your browser. They work just fine in YouTube, but for whatever reason, YouTube and Canvas weren't talking to each other. So that's the plan for lab this week. I'm going to show you here in just a second one of the sensors you're going to use for part of it, and I'm giving you the results. That's what the CMBL file extension is, the logger profile, and we're going to see how that works. All right, so any questions on my quick introduction and keeping people abreast of what we're doing here? Chapter 2 here, what's expected for every class, and this is the lab and for this week. And next week, it'll be a free fall. You'll be dropping a ball. Next week, you're going to need a camera. Of course, for this week's lab, since that's a logger profile, if you haven't downloaded Logger Pro yet, following the instructions that are also in Canvas, let me scroll up and show you where those directions are in case you've lost them. Okay, under syllabus and schedule, distribute Logger Pro, that's the instructions you get to download your free copy of Logger Pro onto your personal computer. And we have a site license at Washington College. Don't pay for it. It should be free. If there's any problem with that, you can send me an email, and I'm going to refer to Dr. Tech, who's our guy, he interfaces with Logger Pro in the Vernier company, and we'll get it squared away for you. All right, any questions on any of that? Good, then I'm going to shift screen share, and I'm going to show you a little bit about Logger Pro here and the sensor that's used in the lab, because it's exactly pertinent to what we're talking about today, what you looked at in the reading before class, and that is graphs of, and if hopefully you're seeing, this is a Logger Pro screen. The one that is in the lab for this week looks very similar to this. I was playing around before class. I'm going to repeat this data, and I'm not sure you can see my video while I'm sharing a screen with you. I'm hoping you can. What I've got right here is what's called a motion sensor. Okay, if you look on the front, it's got this it's an ultrasonic transducer. And I talk about this in the lab video, so if you don't get it all, that's all right. What this does is send a pulse out. It reflects off some object, and the system knows the speed of sound, and it measures the time. And from that, it gets a distance point. And that's what's being plotted on this graph here. And so if you look at the position graph that I did, and let me show you, I'll take another set of data here. This one was pretty good. I was proud of it. I just want to make you see I can do this, but we'll do it again. All I've got is just a piece of cardboard here. You can see it's got a hole in it because it was meant to be seen through. And I'm just going to move the object, okay? So I'm going to hold it still. So if you're thinking about a motion diagram, that's a bunch of dots right on top of each other at, say, maybe 1 second apart. I'm going to slowly move it away, and then I'm going to hold, and so then it's the dots will be about equally spaced, I hope, every second or so. And I'm going to hold it, and there'll be a bunch of dots right on top of each other. That's the motion diagram. And let's see how the Logger Pro sensor plots that. Over in the corner here is a button that says collect, okay? I'll hit that. Start taking data, move the thing away, and hold it. And I guess my hand's a little jittery now. Let me try it one more time. Where that's supposed to be a straight line right there at the top. Let's do it one more time. Move it away. It's a little better. And I'll just hold it till the thing's done, 5 seconds. Okay. And this is the power of Logger Pro, I think. So it's converted that motion diagram to a graph that I've called over and over again in the video, position versus time. Anytime we say something versus something, the first thing goes on the y-axis, so it's position versus time, ordinate versus abscissa, right? If you like those terms in math. Vertical axis, horizontal, position versus time. And you can see right along here, I'm not moving it. My hand's fairly steady too. Okay, so the piece of cardboard was very steady there. And then as I moved it with a constant speed, you can see that the position goes, reading off the vertical axis here. I started, that's 10 centimeters, 30 centimeters, maybe just a little under 20 centimeters, maybe 19 centimeters is where I was holding it. That's about right. I was about that far from the position sensor, about 20 centimeters, looks like just a little less. And then I moved the cardboard until just a little over 50 centimeters. So I guess my displacement will round off to 10 centimeters to 50, about a 40 centimeter displacement. And that happened over a time interval you can see, let's see, 1.2, 1.4 seconds. Oh, let's see, probably about 2.2 seconds roughly. This is a little glitch as my hand probably moved, not being a steady-handed person, I guess. And then at about 2.2 seconds, so a time interval about 0.8 seconds was how long it took me to move that cardboard, a displacement of about 40 centimeters. And so you can, in your head, do the math on that, couldn't you, on what the speed is. This is the cool thing about Logger Pro now. One of the things you should have picked out of yesterday's reading is if I find the slope of this portion right here, what should it be? And no, you don't have to answer that. It was kind of a rhetorical question, but you should find it's the speed, okay? And by the way, once I hit about 2.2 seconds, then I was just trying to hold the cardboard steady. You can see I jiggled it a little bit at the end apparently, and so we'll just ignore that, okay? Hold it still. Move it, hold it still over this diagram. And now, this is the great part about Logger Pro, and you'll either learn to hate it or love it, I guess, but I can do a linear fit, just literally just see where it says linear fit right up there at the top, click on that button, and the equation for a straight line, you should know from an algebra class, is the position, x here, what's on the y-axis, is equal to the slope times the time plus the intercept. I don't really care about the intercept, but I do care about the slope. The slope is 0.4399. And now it's time to answer that rhetorical question. It's kind of interesting. It's rise, displacement over run time. The units are meters per second. Right there, that tells you the answer to what is the slope of the position versus time curve. The units are telling me it's velocity, and it is. Okay, and so you can see here, while I was moving that piece of cardboard, I was moving it with a velocity of 0.4399. I wouldn't use all those digits. I'd probably go to 0.44 meters per second. But the system is willing to say it's displaying to 4 digits. Okay, and so then we'll go down to the velocity diagram, and it's uniform over that interval of time, right? And if you look, the velocity is 0 while I'm holding the cardboard still. And you know, it's funny, in our textbook, everything makes nice, sharp 90-degree turns because that's the way you can do things on a blackboard or in a textbook on a piece of paper. In real life, it took a while to get to that 0.44 seconds. But if you read right across here, there's one, there's zero point 0.2, zero point 0.4. Yeah, it is believable. It's just a little bit over 0.44. It's fairly constant, as well as I could in moving the cardboard at a constant speed right there. And so what I would have you do is just check that. There's also a statistics package right here. And over that interval, you can see that the mean speed, well, in this case, it's 0.4379. Again, almost 0.44, and the units there are meters per second. It just averaged that fairly, boy, I'd love to see it as a perfect plateau, but over that range right there, I've got an average velocity of about 0.44 meters per second, okay? Reasonably checking with the slope of the position versus time curve, which is of course what we want. You'll see this again in lab on Thursday. You'll be able to do an analysis of the logger profile that I gave you for a cart that's moving with a constant speed like this. And that's about all I want to show you on this. Any questions on Logger Pro? Isn't it kind of cool? Remember how tedious it was to find slopes in an algebra class? All you got to do is highlight, and if you noticed, it kind of makes my screen a little bit kind of a bluish gray over the region of data points, which it's going to do the average or the slope over. One other thing I should point out, I think I have the apparatus set up to take 20 data points every second. And so you can see over this, looks like 0.2 of a second. Nope, I'm sorry, 0.4 of a second between these two brackets. That actually is 11 data points, and that's what it's averaging. And so again, you don't have to put those in your calculator. That's kind of slick too, because it averages those 11 data points. You don't have to go over here to this Excel looking sort of column spreadsheet section to do the average. You just tell it which data points to look at, and it'll take care of that for you. If you don't like the data points you're looking, you do have the ability to move these little brackets right here. It's kind of hard to catch them, but you can see I can slide them and I can average different points. I don't like that point right there. Those points, the motion isn't steady yet. Okay, the math is still catching up. But it changes your average as you look at different data points. You don't necessarily want to go from right there to right there. That's certainly where I started the motion, but I wasn't uniform. I wasn't steady yet, right? The velocity hadn't reached its steady value. So I would not do that. I would move these points to where it looks steady right in there. And same thing here. You don't want to take these little brackets to before I started moving. You can see the black line that is the fitted slope. It's all of a sudden not matching my data very well, right? And that's because I'm not looking at the correct data. I only want to look at it where the cardboard in this case, or in your case on lab this week, where the object is actually moving. Okay, so we demonstrated a couple things here. I guess first the Power Logger Pro, and hopefully you'll appreciate that as we move through the semester, because it does a lot of tedious calculations, like figuring out the slope automatically for you. Pay attention to units, okay? We found that the slope of the position versus time curve is indeed velocity, and then Logger Pro was plotting velocity for us, and we can see that we can just take an average over a region, and if it's fairly uniform, that slope and that average velocity ought to agree. Okay, anyway, beyond 2.4 seconds out here, I was trying to hold the thing steady out at this point, some distance, and you can see again back to zero velocity. All right, any questions on that? All right, handy tool. If you've never used Logger Pro before, hopefully you'll become familiar with it. I do know other disciplines use it. I find it like a pretty good piece of software. All right, I want to stop sharing that. We'll come back, and I got to go to my PowerPoint now. So we'll start sharing that. We're going to do some polling here for a second if you don't have any questions, and share that. And where's my first polling question here? There it is. Let's go to that view, and I'll make this smaller so you can see it a little better. Come on, there's this size adjust, make it a little bigger for you. And let me open polling, and hopefully you were reading the question, motion diagram of a car moving along a straight line. And so the question is, which is the correct position versus time graph for that motion? And some people are in here making a decision. And we're split between two. I can see it as you're coming in, and just trust me, for those of you who didn't pick either D or E, right now that is the majority view. Some people are picking D, some people are picking E, and we're a little bit split on it. So if you picked A, B, or C, I don't think you can see the results yet, but trust me, it's not going that way. Think about what you're doing. All right, I'm going to end it, and I'm going to share the results with you. And this is kind of subtle. You have to pay a little bit of attention to what the diagram is telling you. The difference between D and E in terms of the magnitude of the velocity, the speed, I guess, it's going fairly slow for the first, what, 4 dots, 3 dots, then going on to the fourth dot. So you'd expect a lower slope, smaller displacement over a same time interval means a lower slope. And then a bigger displacement for the same time interval means a greater slope. And both D and E have that attribute. The one subtle piece is look where somebody decided to put the origin at the fourth point. So these first 3 points here are to the left of the origin, and so they are negative. And so those of you who went E, you nailed it. Good job, you saw the 0. D would be right if the origin had been put at the first dot. There is no requirement that the origin be put at the first dot. Some people asked on the worksheet from Friday, I guess, are we allowed to have negative times? Are we allowed to have negative distances? And the answer is yes. Oddly enough, that's the work of Einstein. He said any reference frame, either in time or space, any coordinate origin, any time origin, equally valid as any others. That's one of the pieces of his principle of relativity. It doesn't matter where you put it, just do your math consistently, everything will work out. Nothing says you have to start at time equal to 0, position is equal to 0. All right, good stuff here. Let me move on to the next one. Pre-prepared just in case I lose track. E is indeed the right answer. Stop sharing. Go on to the next question. Launch the poll here. Move that out of the way so I can see it. Now, I don't know why I have that thing in the middle. It's just restating the question here. So you can ignore the text in the middle. I don't know why I pasted it in again. The figure shows a position versus time curve. And notice how everything has nice kind of pointy transitions, right? And I want to know what are the location or locations where the object's at rest. And again, I apologize for those words over the diagram. That's C up at the top there. I think I can actually move it. I can delete it in this screen. There, go away. Make that go away while you're answering the question. Where is the object at rest? About half the people are in, and most people are getting this right, so that's good. That's good. Couple more seconds here. Yep, I got everybody in. And poll and share the results with you. And I would just ask you to think about all the places where the speed is 0. Objects at rest, speed is 0. All that's necessary to be at rest is that the position is not changing. And so the best answer is A, C, and E. Right here, you're stationary at a negative position. So that means is you're to the left of the origin. Up at C, you're stationary and you're in a positive value, so you're at the right of wherever the origin is. And in point E, you are stationary right at the origin. Now, if you went with B, okay, B is at the origin, but it's moving. You can see it's along a line that has a slope. So there is a speed right there because the velocity is changing. Just because you're at the origin doesn't mean you're at rest. All right, so we'll move on to the next one just so you can see. Yep, it's A, C, and E. Here's the next question. Let me stop sharing this and open up the next poll. And now I'm asking, same diagram, at which lettered point or points is the object moving left? Launch, and you're off. Too easy for some of you, isn't it? Sorry if it'll get harder for some of you. For those of you that just jump right in, you got this stuff, you've seen it before, or it just makes perfect sense to you. That's great. It certainly makes my job a whole lot easier. All right, 24 people in, just a couple more, 26. All right, we got everybody. And so share results with you. And you can see the majority went with D. Notice that whereas this line right here has a positive slope, that would be motion with a velocity to the right. D here has a negative slope. You're starting at a positive position and going to the origin. Okay, so X is a positive number, you're moving to the origin. Well, that's to the left. And you also have a negative slope. If you were calculating the slope at point D in an algebra class, you would get a negative rise, right? And a positive run. And so that's a negative slope. Negative means we're moving to the left. D is absolutely the right answer. So good job there. Okay. D, yep. Go to this one right here. And I'm going to stop sharing this. Open the next one, number 4. Launch the poll, and this time, same diagram, highest speed. Remember, I didn't say velocity here. I said speed. "22, 23, 27, and everybody's in. All right, we'll end that. And the key word here is highest speed. Okay, as we just said, B is a region where you have a positive velocity. D, the slope is a negative velocity. Okay, and so if I'd have said velocity in the sense that a positive number is greater than a negative number, I would have agreed with B. But speed now is just the magnitude of that slope. The slope magnitude is greatest at D. It is the steepest slope, so that is the highest speed. And so I agree with those of you who picked, there it is, I didn't share it with you. I agree with those of you who picked D, which is the majority right here, because you realized D might be negative, it might be going to the left, but it's going to the left faster than B is going to the right because it's got a greater slope. Everybody good with that? And that's just a technical, a technical term of art, as the lawyers, I guess, would say, for physics, the difference between speed and velocity. Had I asked you which was the largest velocity, B would have been the right answer, because a positive number, of course, is a greater number than a negative number. Stop sharing that. I'll put that up. You can see D is the answer here. We'll move to the next one. I guess I got to go. This is question 5. Launch the poll, and you're off. And this one I'm asking, at which lettered point or points is the object, it's only point here, there's only one choice, lowest non-zero speed? All right, 19 in. What do I got here? This man's sending out emails this morning. All right, one more. Got 27 to 20. There we go. Everybody's in. All right, I'll share the results with you. And for A is still a 0 speed, right? C, still a 0 speed. D, well, that's a large speed, as we said. That's why it was the answer to the last one. B is non-zero, and it is the lowest non-zero speed. Okay, D is the greatest non-zero speed, I guess. All right, so I'm with you on B, and I'm pretty much for the same reason we talked about last question. All right, let's move on to poll 6. Move out of the way, window, and yep, B. And so now we're on the next one, and same diagram. Which lettered point is the object at rest to the left of the origin? I guess I've said this already. "13 people in." And you always got to remember the conventional way to draw a coordinate system, that's positive right there, and that's negative right there, isn't it? Negative numbers. That's a pretty big hint, I guess. All right, everybody in poll, and the majority says A, which is correct. The negative values are to the left of the origin, and so the 24 out of 29 people who said that, excellent. All right, so stop sharing that. And I'll move on to the next one. And yeah, it is A. Here's the next guy. I got to go to 7. Just a couple more of these. Launch the poll. Now we got this position versus time curve. It's almost just, it's similar to the one I did in Logger Pro. And now you've got to figure out what's the velocity here. Velocity time curve from looking at the position time curve. Remember, it's all about the slopes. What's the slope of the position time curve? 5 people are in. I'll tell you 7, 8, 9. Everybody's right so far. So great job. 14 people are in. I can actually draw on these. I keep figuring out more and more things I can do with this e-teaching, this online teaching. All right, 23 people, couple more. Oh, we lost a person. All right, pretty much got a quorum here. I'll end it and we'll share the results. And of course, great job to the people who picked C. Here's why. Look, right there over that region. What's the slope of that line? The rise is 0. That means it's a 0 slope. So that would be either right here, 0 slope, or right here, you got a 0 slope, or right here, you got a 0 slope. So it kind of eliminates A, doesn't it? And then right here, that line has a negative slope, doesn't it? And it looks constant. So it's not constant, so that can't be right. It is a negative slope, and so that can't be right either. So I guess that can't be right, that can't be right. We're left with C, and that's, I think, why you got it right. So exactly the right answer there. Good work. And let's move on to the next one. Stop sharing, move over to 8 here for you. Launch the poll. Now it's a velocity versus time curve. And from that, you have to pick the position versus time curve. So we're backwards here. We're doing it just in reverse of what the previous question had. Yeah, a little harder this time. I could see some people. It's interesting. It's not showing me the bar graph for D. I can only see the bar graphs for A, B, and C right now. I've got about half the people in.
I think we can see the answer to this at the bottom of the screen.
Really?
It says answer D.
Oh, I hate when that happens. Which screen? On the polling screen or in the?
On the PowerPoint.
On
I
the
think
PowerPoint.
it's in your notes at the bottom.
Oh yeah, I got it. Okay, thank you. Let me see if I can hide that. Let's try there. Can you see it now?
No.
Okay, so that's the way we'll launch these. That way you can't cheat on it. Cheating is a strong word. All right, looks like everybody's in here. Hey, thanks for letting me know that. I'm learning these things as we go. All right, and share results. It moves things around a little bit, but 25 of you went D. And just so we're clear on the Y, right there, that's a constant velocity, constant speed, and it's positive. And so you can see you've got a positive slope on D until you hit the point where the velocity goes to 0, and then the particle just stops wherever it is, right? And that's what happens here. All right, let's stop sharing that. Let's go to the next one. And we're on 9 here. Let me shift over to 9. Launch the poll. Do you see the figure?
No.
All right, let me go to the next one. Okay, so that for some reason it's in there twice. That's still number 9. So that's the one.
You still can't see it.
Still can't see it. Some people can. Without showing you the answer, let me go back, forward. 10 people are seeing it anyway. It might not have updated for you. All right, looks like we got 24 people in. All right, I'm going to end it. 27, one more. All right, this one's a little bit different in the sense that it's curved, right? We don't have those abrupt changes like right at the corners here, okay? But what would the slope be at point A? Well, 0. What would the slope be at E? Well, just for a second there, it's flat, 0. And so I would agree, sharing the results, with the majority who picked A and E right here, the 21 of you, because, yeah, that's where, at least for just an instant at E, there's no slope. There's 0 slope. Positive slope just before E, negative slope just after E. Okay. Of course, B has a slope, C has a slope, D has a slope, F has a slope. A and E fairly flat. E just for an instant, just for a very short period of time. What we call the instantaneous velocity at point E, or the instantaneous speed. Stop sharing that. I think we just have one more. There's our answer. I don't know why I got an extra slide right there. All right, and here's question D, or question 10. And bring it over here and launch it. And now we're not seeing the figure again. It's the same figure. I don't know why I've got an extra one there. Can you see the figure? Same one again. And this time we're asking at which lettered pointer points is the object moving with the highest speed? And I can tell you this one's close. I think it's close. So you're judging where on that curve is the slope the highest. The majority of you seem to have it though. All right, one more person in. Come on, last person. Give me another second. We got to move on to do some problems. Yep. All right, and I'll share the results. And most people are saying C, and I agree with you. I think C just has a slightly higher slope than at either B or D. Okay. B, if I drew the slope, it'd be just a little bit less. D would be just a little less. So I agree with C. And by the way, I think F would have the same speed as D, but of course, F is moving in the negative direction, moving to the left because it's a negative slope, whereas D is moving to the right. But they look fairly symmetric and they probably have about the same slope. Didn't ask a question on that, but I wanted to point it out. Stop sharing, stop sharing. And I think we've had enough fun with polls here this morning. So let's go on and solve a couple problems. And let's see. Let's open up the worksheet. You want to do time dilation? No, that's my other class. X and Y graphs. Open that. Stop this. Escape out of there. And I promised I would do one of these problems, and I'm going to try to do it right here on the screen. This is the worksheet for today, I believe. Yep, 2-1, position and velocity graphs. Let's share that with you. And just because I'm running a little short on time, I'm going to just try to write with my mouse here. I think I asked you guys in one of the early the survey the survey that we did on SurveyMonkey. I asked you, how's your writing with your mouse? Mine's getting better. That's all I'll say. And I think I advertised that I was going to do problem 5, and you then would be doing 1, 2, 3, and 4. And by the way, 3 and 4 are really the same problem. And so quarterback Bill here, I don't know, make it Peyton Manning if you like, make it somebody else. Oops, come on back here. I hit the wrong button. There, I need to draw. I'm gonna go obnoxious red. He throws the ball to the right at a speed of 15 meters per second. It goes for 45 meters, and then it's intercepted by Carlos, who's running to the left at 7 meters per second. Carlos carries the ball 60 meters to the score, and then to score the touchdown. And let's let X be equal to 0 where Bill throws the ball. Okay, and we need to do a couple calculations before we can actually draw the diagrams, I think. And the first one is, okay, ball's in the air, and he's throwing it with 15 meter per second speed, and it goes 45 meters before it's intercepted. And so I guess, how do we find out how long the ball was in the air? Well, remember the velocity. I'm going to drop the subscript here. It's in the x direction, is just delta x over delta t. And so if I'm looking here for the time interval, delta t, well, what I learned for ratios is if you interchange the means and the extremes here, there is no denominator on the v, it's just a 1. You can do that and you haven't changed the ratio. So I've got delta x divided by the velocity. Displacement over the velocity is the time interval. Now, I'll tell you, in a physics class, grading over 20 some years, the biggest mistake here is people get the velocity over delta x. If you check your units and you make that mistake, you'll catch yourself. If you don't, you don't do unit analysis, you're running without a net. You might get it right, but if you make an inadvertent mistake sometime, you have taken away your safety net. And so in this case, I've got 45 meters. Oops, that's a lousy looking 5, but that's the way it came out, divided by 15 meters per second. And I think I told you on day 1, you do these problems twice. 15 divided into 45 is 3. Got that right. But then a meter divided by a meter, meters cancel. And I've got 1 over seconds. Something in the denominator of the denominator is in the numerator. And so sure enough, 3 seconds is my answer. Okay. And hopefully this equation is good for you. You can do it. And then how long is Carlos run to the end zone after intercepting the football? He carries the ball 60 meters to score, and his speed is 7.5 meters per second. Exactly the same calculation. I'm going to call this Bill. I guess that's the time for Bill to throw the ball. This is the time for Carlos to run. And so the displacement here for Carlos running, I think, is best said as minus 60 meters, right? He intercepted the ball and went the other direction. So if Bill threw the ball 45 meters in the positive direction, well, when you intercept, you run it back the other way. So that's minus 60 meters per, we divide it by a speed of 70.5 meters per second. But this is also negative, right? Because this 15 was in the positive direction. Carlos is running in the opposite direction. Okay, again, 60 divided by 7.5. I did that on my calculator last night, so I know that's 8. And then the meters cancel, and sure enough, I've got seconds, and it turned out to be positive. Okay, and so now I want to draw a velocity versus time curve. I could have done that first. I have the 2 speeds I need. I just didn't know what time intervals here. So in order to make this time in seconds and this velocity in meters per second, and on any graph you draw in a physics class, you need to label the axes with the units that you're putting on them. Let's see, there's about 3 seconds right there. And let's see, and then Carlos goes for an additional 8 seconds after that. So I guess this will be about 11 seconds right here. 3 plus 8, 11 seconds total motion. Okay, so first we start with a positive 15 for the football. That's coming out of Bill's hand. So it goes 15 meters per second for 3 seconds. And then I never know what to do right here because, as I said, it's an immediate change. But then Carlos intercepts the ball, and for the next 8 seconds, he runs, and I'm trying to draw about the right speed, about half. So he's at negative 7.5 here. So that's 7.5, and I'm making that 15. And so I'm trying to make it about half the distance. Right here, that's 15. Right here, that's 7.5. Everybody okay with what I did there? Excellent. And so then the next thing now is from this, I want a position versus time curve. And so again, time in seconds, and then velocity in, oops, nope, I'm wrong. Let's get my eraser out here. That's not velocity, that's position. So that's, say, we'll call it X. That's what I've been calling it, in meters. Okay. And the ball starts, we said in the problem, zip right on up here. Let X equal to be 0. X equals 0 be the point where Bill throws the ball. So that's where the ball's motion starts. Okay. I need the 3 seconds right here. And we just decided the ball goes 45 meters before it gets intercepted. And so over 3 seconds, straight line, and that distance right here would be 45 meters, right? Okay, then Carlos intercepts the ball, okay? And for the next 8 seconds, out to 11 seconds, Carlos runs 60 centimeters, I'm sorry, 60 meters. If I've been saying centimeters, I apologize. 60 meters back the other direction. So this is 45. He goes 60 back the other direction. So the goal line must be 15 meters behind Bill there. And so his endpoint is right about there. And so that's the motion, and it's meant to be a straight line right there. For Carlos, after he intercepts the ball, he runs in the opposite direction as the ball was thrown. And hopefully you can see that this slope right here is greater than this slope right here. It would be if I made a better sketch, I suppose. Any questions on that problem? All right, pull out that piece of paper. I guess we got about 5 minutes here. And here's what I'm gonna do. I always give the extra point question. Okay, so the first person who posts in chat, problem 1A here, how long does it take this parachutist to reach the ground from 1,500 meters at a speed of 5 meters per second? And that's downward, obviously. All right, so the first one in, I see it already. Elena, you win. Kyle, she beat you. 300 seconds is the right answer. It says Stephanie. That's Luke, isn't it? 5 minutes works for me too. But the first person in here was Elena. And so now you just got to use that to draw what your graphs were exactly the way I do. But with that time now, you kind of know, oh, we're going to put 300 seconds, or as that's Luke, I think. Using your sister or mom's computer or something. 300, and that's time in seconds. Used to be camo person, weren't you? All right, you change these things up on me. It's hard. Now, what are we plotting here? We're plotting position. You can go Y if you want on this one, right, in meters. And you know where the starting point is, so draw that curve. And now, from that, once you've got that curve drawn, and she's floating downward, right? And I just want to point out, most people, when they draw a Y-axis, they make positive up here and negative down here, right? That's pretty conventional. It's not always true, but that's what you'd probably want. All right, so now that's from that, go ahead and make a sketch of velocity versus time over that 300 seconds, that 5 minutes in which she's parachuting down. Your name is Stephanie. Okay, cool. We'll have to talk sometime. Don't I have a loop though? All right, well, we'll figure it out. All right, hopefully you've got that done. And so now I want to go on to problem 2, and pretty straightforward here. you got two position versus time curves, A and B, and I'm simply asking at the time 1 second, which one's going faster? Is A greater? Is B greater? I guess are they the same? And just take a second to explain why that is. And then the next question, do the objects ever have the same speed? If so, when? If not, say they don't. All right, give you a second to think about that. And we'll move on to the last two, really, I guess. And now you're just drawing curves. And so you're starting with a velocity versus time curve. And you can see you've got a positive velocity out to this point right here. And I'm just trying to draw it right below there. Okay. And then what do you have here? Then you have zero velocity. And then you have a negative velocity out to that time right there. And then you have zero velocity. And so what you have to do right there is construct the position versus time curve. And I'll help you out with the first piece. Right there, you got a positive velocity. That would mean a constant positive slope right there out to that point. And you get to draw the last couple of legs. And I think my time is just finishing up here. I got us 2 minutes over. Then the last question you have to do is, what's the total displacement now? And remember what we said, displacement is the area under the velocity versus time curve. And so it's those areas right there. And so what's the total displacement for this problem? And you can just say a word or two why. Yeah, it is significant. You don't have any numbers on this. So you just got to kind of look at it and do your best estimate. Hey, that's it. Any questions for me? All right, then I've kept you 2 minutes longer, but I'm getting this timing stuff down a little better so we can go over the worksheets, and you don't have to pop it in your solutions here, the things you've just drawn, but before Wednesday's class, please upload that to Canvas so I can take a look at your work. I'll stop sharing and wish everybody a great rest of your Monday, and then we'll see you all Wednesday morning for more of this stuff. Have a great day.
Thank you. Have a good day.
Thank you.
Hey, Professor.
Yeah,
I have a question.
sure.
Because I did the what is it? The primer, I think it was.
Yeah.
And there was a problem that had us convert kilograms over meters per second. No, kilograms over. Maybe it was kilometers over meters per second to. No, wait. That's not right. I gotta figure. Let me pull it up really.
Yeah, go ahead and pull it up. This is office hours. I was just going to go refill my coffee cup, maybe go throw it in the microwave to heat it back up. And so I'll be starting office hours at 9:30. But if you just got a quick question, we can take care of that right now. And I think I can let you share your screen too. Hang on a second here. Let me pull back so you don't have to get so close to my ugly face here. Security. I think it's under security. Allow participants to share screen. I just checked that box. So once you pull it up, that green button that you should see that says share screen, and then just point to it, and I should be able to see it.
Okay, I lied. It was actually in the problem set.
Okay, that's fine. Yeah.
So it wanted us to convert the millimeters into meters, and I was really confused as to why it becomes a bigger number.
Yeah.
Because in the hints, it said we would go to -9, which made sense to me because millimeters is smaller than meters.
Okay. No, I completely got it. Let me give you the common sense version to kind of get a picture. Can you see me? Is my picture still in your screen?
Yes.
Okay, so think about a millimeter cubed. I mean, it's so small. I can almost think about a centimeter cubed, and then make that even smaller. So a millimeter on a side, and in that millimeter on a side box are jammed in a fairly small amount of mass. If you think about it, 10 to the minus 6 kilograms is 10 to the minus third grams, right? Can you do that part in your head?
Yeah.
Okay, so that's like I think doctors call that a milligram. Like a lot of dosages of medicines are milligrams. So it's a milligram in a millimeter cubed. Okay. If you were to take it to a meter cubed, now you got a box that's like that. Think about how much mass would be in that box. It's going to be a huge amount of mass. Okay. And so that's what I'm expecting. So there's just on a common sense idea, I've made the box from 1 millimeter on a side to 1 meter on the side. So I expect that amount of mass in that meter cube box to be huge. Okay. So that's kind of my instinct, my expectation. Now let's look at the math, I guess. And I'm going to write down the number here first. And then I'm going to switch over to my whiteboard so I can show you all the steps. Okay, and let me get the number down. 5.23 times 10 to the minus 6, and that's kilograms per millimeter cubed. All right, and so now we'll stop sharing that. Can I unshare you? Yeah, let's see if I can do that. Yep, okay, continue. And then I'm going to share with you my tablet, which means I got to take a couple steps here to do screen mirroring. Come on, you can talk. Maybe not this morning. It's not going to play. All right, well, that's whiteboard 1. No. Let's now go to stop. Up. Did it do it? Nope, still not seeing it. I got another whiteboard, though. We can solve this. I just have to write with my mouse then. iPad, you're fired. Okay, hopefully, can you see my whiteboard? Your screen, yeah. Okay, and so let me get that number down here again. 5.23 times 10 to the minus 6 kilogram per meter cubed. That's supposed to be a kilogram. No, that's minus 6, isn't it? Minus 6 kilogram. I'll make the units big per meter cubed. Millimeter cubed. All right, and what are we supposed to get it to?
We're going to kilogram meter cube.
Per meter cubed. Okay, yeah. So I don't do anything at a kilogram. So the first thing I do is I got to go, what's a conversion between millimeters and meters? And so I think there's 1,000 millimeters in every meter. Agree with that?
Yeah.
Okay, so in order to cancel, I need the 1,000 millimeters to be in the numerator and the meter to be in the denominator. But here's the deal. That's cubed, isn't it?
Mm-hmm.
So this has to be cubed. And then that unit right there and that unit right there will cancel. All right, so we're rolling here. What is, it's almost easier for me to write this in scientific notation. Your calculator will do the job right from here, but that means I have 5.23 times 10 to the minus 6th, and then that's 10 to the third, 1,000 cubed, right? And the units I have left are kilograms divided by a meter cubed. All right, well, 10 to the third, I think you said something about 10 to the positive 9th, and it is, right? Because you multiply those exponents. Mm. And then I've got 10 to the minus 6th right here. And then I've got 5.23. Okay, I already got the 10 to the minus 6, bring the units down. And now what do you do to the two exponents in the scientific notation here, the 9 and the minus 6? They add, right? And so that's 10 to the third. So 5.23 times 1,000, essentially, kilogram per meter cubed. And so that you can write it that way if you want. That's the same as 5230. This 3 right here says you move that decimal point over 3 points, and that's the answer right there. Does that do what you needed?
Yeah, I think I had just gotten so hung up on the idea that it had to be a smaller number,
Yeah.
because if you're going from millimeters to meters, you're going backwards normally. So I was,
Your answer just didn't make sense to you.
yeah, well, because I kept trying to put it in different ways, and I was just like so confused because like I figured that it was supposed to be smaller, but I didn't think about it logically with like, since it's a larger size, it can
Yeah.
hold more.
Yep, that's exactly the way to see it. And I hope you can see that that's the little box that's 1 millimeter on a side, and this is the box that's 1 meter on the side. Which one's holding more mass? Much more here. And by the way, this isn't even a scale, right? I mean, this side right here would have to be 1,000 times that right there. So I haven't even got the scale right yet, but it gives you the idea.
Yeah, thank you very much, Professor.
All
I
right,
appreciate
cool.
it.
Have a good day.
You as well.